everyone. Hello everyone. In this video we are going to see about uh, some application of superconducting devices such as Squid, superconductor quantum interface device and magnetic levitation. These two applications are the basis from the superconducting materials. So just recall about the superconductivity. Superconductivity is nothing but it is the material behave superconductivity at below some elements below the critical temperature. That's we have seen in previous video. So that will be reason for the magnetic levitation. So Meissner effect state that some of that materials expels magnetic lines of force in below critical temperature. That is called as a Meissner effect. So in this just recall we have to say about another important theory about the superconductivity, that is BCS theory, Burton, Kobach and Zuckerfeld theory of superconductivity. It tells about that the electron formation, electron pair, that is Cooper formation, is reason for the superconducting nature of this particular materials. So these are the picture diagrams shows that is materials behaves magnetic levitations and the Cooper formation in the lattices. So the electron pair moving through the lattices because of that phonon interactions. So in this topic we are going to see about some understanding of superconducting quantum device, that is Squid device and Maglev trains. These are the main commercial applications in these superconducting applications in these real world applications. So these are the pictures indicate that superconductors are mainly used in what is that we have to know about the MRI scanning. MRI scanning, it is the based of superconducting quantum interface device and some of Maglev trains, and recently we have developed some of the superconducting conductors materials will be used for in a quantum computing fabrication devices. So these are the enormous amount of superconducting materials used in various industries in real world and technology developments. So these are the schematic diagram of a cubic Squid diagram, that is nothing but superconducting quantum interface device, and you can see that you can see that the circular image is called a superconducting coil, and there is a junction is called as a quantum interface junction, or it is called as a Josephson junction. So there is a magnetic lines of force in between that coil. So the coil is made up of superconductors. It is kept in the below critical temperature, that is a transistor temperature. The magnetic lines of force are expulsed. So device, there's a junction called as a Josephson junction. So once the superconducting coil is fabricated and below temperature, it is expels the magnetic lines of force. When we pass the current to the superconducting coil, it will create magnetic lines of force, magnetic flux around the coil. So this is the detector, which will in between that there is a gap or Josephson junction which is made by the insulating materials. So the device is used as the sensors that will be used the principle of quantum tunneling effect by the particles, that is especially in this case electrons. So this device is placed on the MRI scanning. There is the very minimum changes in the electric field or the brain cells of the neurons. It will indicated by the Josephson junctions. So that's a small change in the electric functions, electrons function or magnetic flux change indicate that the electron jumps from the one junction to the Josephson junction to the another coil. So the small variation will be detected by the superconducting interface device, that is used as a detectors. So that's why the Squid device is most useful for the fabrication, most important for the fabrication of sensor devices. So these are the working nature of the Squid interlaced devices. Next we have to see, these are the schematic diagram. This is you can say the Cooper pairs across the junction of the superconducting coil, that is a quantum tunneling effect. So these are the cubic voltage will be applied across the superconducting coil, the Squid device. So we can calculate the voltage between the junctions. We can identify the changes of the produced by the small fluctuation in the magnetic fields. So in this, you can change that from the signals. We have to analyze. So where the deflection, where the output, where the input, we have changes will be interpreted with these input values. Next is the one of the main applications is the Maglev levitation. So it is nothing but a schematic diagram shows the electromagnet, which is called as a supermagnets or supermagnetic fields. So there is a Maglev train is using the repulsion force and as well as attraction force. So track will be based on there is a small amount of small bars of magnets where super magnets were placed, and similarly we have magnet will be stored on these maglev trains. So the track cannot be the high speed which will be achieved by this floating method. So there's a U clamp is the protecting, and it is suspended over the air about some of 10 mm. So the train will be frictionless to get achievable speed to maximum speed. So it is the repulsion and propulsion will be made by this electromagnets will be, that is called as supermagnets. We can change the polarity of the magnets, it will propel or it will propellate, it will accelerate, or it will reduce the speed of the trains according to the input voltage. That is, we have to electromagnets, supermagnets will be controlled by the current. So we can increase the speed of the train or we will reduce the train of speeds. So this is will be completely, it's a frictionless. The train will be suspended over the track. It's some about approximately 10 mm distance. So this is the maglev train, the schematic diagram of the maglev train. This is the levitation will be used in the maglev applications. So in this video I stopped here the basics about the Squid and maglev applications. Next class we have to see about the very interesting applications and deep into that Squid and magnetic levitations, as how much is working in the sensors and application point of view. Thank you.